Hello students, good morning. As you know that we were doing atomic structure, the chapter, and we'll continue with this chapter because still some of the important points and the portions are left out. So today we will be doing something interesting about this chapter, that is about, as the name itself says, atomic structure. So we will be doing about the structure. Now this the structure is regarding. Previously, you have already you have done about the structures regarding considering the different orbits. So now today we will not focus on those orbits again. We will do a new approach. We will consider take up a new approach of representing a molecule. The molecule can be of an element. The molecule can be of a compound. But whatever it is, we will consider. We will take up any of the molecule and we will represent the molecule in a slightly different way. And what the way is, so we will move on to that one. So today's discussion will be on that particular representation. It is called Lewis diagram. It is called that, as I said previously, that a new way of representing a molecule. Beforehand, we have already discussed about the representing a molecule in terms of rather electrons and the protons and the neutrons. And with the center part it's having, we will go and start with the nucleus with the protons and the neutrons there. And we will move on to go with the distribution of electrons in the different energy levels or energy shells called orbits. Now, these orbits are basically also called as the electronic distribution and the orbital diagram. As it's represented over here, it's called the Lewis diagram. It's called, you may pronounce this word or as a Lewis, or you may also pronounce this word the Louis. No problem. The It's basically after this name is after the name of the person itself. The diagram has been, you can understand by the name by the, of the diagram, Lewis diagram. This Lewis diagram has been discovered by the person, Lewis itself, and the name has been given after him. Now we need to know what is the first thing we need to know, that is, what is a Lewis diagram? The first question, of course, is when we come across new words, then definitely the first thing we need to know that what is rather the meaning of the particular word is, what information that word provides. Now the first question, it's a genuine question, what is a Lewis diagram? What's the answer? The first thing, it has been named after Gilbert and Lewis and is called also termed as electron dot structure. So it's named after the, as I said previously, by the name it has been named after the person itself. So Gilbert and Louis, he discovered this one probably in around 1930 20s that time. That he proposed that there should be a new way to represent molecules, not going because this in a different method, of course. Also termed as electron dot structure. Why we will call electron dot structure, we will come to that one also. Now, Lewis diagram is basically diagrams that show the bonding between atoms of a molecule by considering the valence electrons only. That means, so as it's saying, that diagrams that show the bonding between atoms. Suppose we are having a different, we can represent the diamolic bonding between molecules or bonding between atoms by considering the different orbits also. But as per Lewis, his proposal was that we will only consider the valence electrons, nothing else. Okay. The diagram also shows the total number of electrons that are bonded and non-bonded, that are bonded, and the non-bonded electrons also. What information apart from diagrams we will represent by the electrons which are present in the valence shell called the valence electrons, followed by the diagram also represents that how many electrons are bonded and how many electrons are non-bonded. That means how many electrons are participating in the bond and how many electrons are not participating in the bond formation. Bond with whom? Of course, to form a molecule. That molecule can be to form the molecule of an element, and that molecule can be of a compound. So when in terms of also for compound formation, the molecule is formed. So bonds between atoms of a molecule, atoms of a molecule of an element or a compound, whatever it is. So the non-bonded electrons are also represented. The non-bonded electrons are termed as lone pair of electrons. So either lone pair only. We can normally when we are having a colloquial discussion, then we can normally see how many lone pairs are present in a particular atom, or we also state that how many lone pair of electrons are present. So both, if I say it's a lone pair of electrons, that's scientifically correct. The colloquially, we normally, when we are having a discussion about these electrons, the non-bonded electrons, we normally say how many lone pairs are present. In the question also sometimes it comes at how many lone pairs are present in a particular atom or in a particular molecule. So it is called the lone pairs. So lone pair of electrons, or lone pairs of plural also, both anything. So if it's a one pair of electrons present, then only lone pair. Multiple, if more than two pair, rather four electrons present, then two pairs of electrons. So two lone pairs are present. Okay. Now lone pair is atom-oriented, not molecule-oriented. That means it's basically a particular molecule will have how many lone pair of electrons that depend upon the atoms which are, or rather atoms which is forming the bond. So the atoms which are undergoing bond formation and with other atoms. So those particular one important atom, the central atom or the bigger one or whatever, the bigger atom who actually participates in a lot of bond formation are only those atoms which are having excess electron. That means excess means those atoms who are having electrons rather more than 3. So atoms who are having electrons more than 3, they only and normally um, they normally have lone pair of electrons. So how many lone pair of electrons a particular atom will be having, that totally depends upon the atom itself. So it's not a molecule dependent, that this particular molecule will have this. So it depends upon the atoms. So while the molecule is being formed, or rather after the formation of the molecules itself, it depends or based on the bigger atom and the atom having the excess of electrons in the valence shell. It depends on that, how many valence electrons, or rather how many lone pair of electrons will be there in the molecule together. That will be governed depend. All right. Now the question is why electron dot structure. Okay, I'll come to that one also later. You'll understand why it's electron dot structure. Coming to the next, that is representation of molecular structure. What are the different ways of representing a molecule? The first is orbital structure. We know that. We have already discussed that one earlier, that what are different methods probably of representing a molecule. The first is the orbital structure, and the second is the electron dot structure. What is an orbital structure? In the orbital structure, the structure of the molecule is represented on a two-dimensional surface. Over here, the word two-dimensional surface is specified for the purpose that We normally represent that one either on a piece of paper or any flat surface by drawing, hand drawing. So on a two-dimensional surface, where we represent the molecule of by considering the different orbits. So what we do normally consider over there on two-dimensional surface, we consider the orbits. So the central part of the nucleus surrounded by the orbits, and the electrons present in those orbits corresponding to that of an atom. So the first, so we will on the two-dimensional surface, the nucleus at the center, followed by the orbits surrounded, and every orbit having certain capacity to accept or hold electrons. So those electrons will be presented over there, and we know, as we know that every atom is having a difference, maybe in the number of orbits same, but the number of electrons differ. So based on that, and the number of protons and the neutrons differ with every atom, with every element. So for that reason, orbital structure is normally considers the orbits followed by the electrons present over there, and which is atom specific, as well as the central nucleus. Now, what is an electron dot structure? Only the valence electrons are focused, represented by dots. That means in this structure, we will only focus on the valence electrons. Okay, so we will only focus when we are representing the structure of the molecule. Only the valence electrons are being considered while representing the molecular structure. And how the valence electrons are represented? By dots. By dots, nothing else. You make it similar to a full stop. That's all that, like that, dots. So the electrons are represented by dots, and only the valence electrons are considered. And then followed by how the bond is represented, how the bond between a molecule, between the atoms of a molecule are represented. There lies the question, and it is being shown accordingly. That means in the following, when we will go to, as we will move on to our lecture, we'll definitely show that how it's working, it is being represented by, and hence it's called an electron dot structure. Now, why the electrons of the valence shell is being considered? What was the basic idea of Lewis behind drawing or representing a molecule behind, or rather molecule, as by electron dots, or rather by this structure? What was the basic logic or the idea, motive behind this one? Number one, if it is represented by dots, then definitely it will save space. So to make the molecular size smaller, or rather representation of the molecular structure in a very small space, it is done. That's the first point. The second very important point is Lewis had a concept that if, and that's what's true, that's what's correct, and you know also that since the valence electrons participate in a bond formation or in a chemical reaction, since the valence electrons participate in bond formation or a chemical reaction with other atoms, thus the inner electrons and the central nucleus having no role in during chemical reaction or bond formation, thereby only thus in a molecular structure where the bond formation is important, that how the bonds has been formed, and the representing the bonds together. So under such conditions, only the valence electrons play the major role, and the rest of the electrons present in the orbits of the molecule, or rather the atom, orbits of the atom, and the central nucleus is having no role. So mentioning or highlighting them is actually a waste of time. It's a waste of space. So if the structure can be represented in a very small place where all the bonds can be shown, then that will have saved a lot of time, and it would have been easier to understand also. without going into the details of how many protons present, how many neutrons present. That's not so important. Not so important while representing the structure. So, with the central part having the atom symbol followed by the valence electrons around it. Now, we will start with how to draw the Lewis structure. That's a very important question. Now, after so much of the discussion, how to draw the Lewis structure. So basically, there are all total 5 steps. If you follow the 5 steps, it's not so, I'm just telling you out, it's not so difficult. It is not at all difficult, it's not so confusing, but only thing, just follow the steps as it has been mentioned in the lecture. And as it has been shown over here, that and the steps are written also, just try to follow those steps. That's all. That's all. And Lewis structure is a very, very simple thing. It's very simple. Okay, so let's get started. The first we will consider this example as in the form of a question. The draw the Lewis structure or electron dot structure of sodium chloride molecule. Draw the Lewis structure or electron dot structure of sodium chloride molecule. Okay. Now, sodium chloride molecule, the first step, list all the elements present in the molecule. Clear? This is the first step when we will draw a Lewis structure or electron dot structure. So we will first list all the elements present in the molecule. What are the elements present? Sodium and chlorine, these 2 elements present. Step 2. List out the number of valence electrons present in each atom of the elements. Now the step 2 is list out the number of valence electrons present in each atom of the element. Just the valence electrons. So we have written atomic number of sodium is 11. Number of valence electrons 1. Atomic number of chlorine 17. Number of valence electrons 7. Okay. So step 2, I hope it's clear till that. All right. Moving on to step 3 now. Write the molecule in a formation reaction form. What is this formation reaction form? Like this way, as it's shown, Na, symbolical, plus Cl, chlorine, gives NaCl. So this is, we will write the molecule in a formation reaction form. So our target is NaCl, but we will write this one as if Na plus Cl giving NaCl. The same as in a similar way it's written in the formula, nothing else. Now coming to step 4. Draw the electronic structure of the reactants using dots. Draw the electronic structure of the reactants using dots, where dots represent valence electrons and without considering the other electrons of the orbits. I mentioned this one, that's the electrons represented by dots and only the valence electrons, of course, and we won't consider the other electrons which are present in the molecule. We will not consider the other elements or other electrons which are present in the other orbits. Only the valence electrons present are in the valence shell. This is how it's represented. Sodium with a dot, as you can see, is electron dot structure of sodium. This is chlorine, as you can see, 7 electrons, 7 valence electrons. That's chlorine. Okay, 7 valence electrons. That's an electron dot structure of chlorine. Clear? Simple? Now, over here, since chlorine and for distinguishing, in order just to distinguish between the electrons of Na and Cl after the bond formation, for that reason, Na has been represented by a different color. It has been highlighted, nothing else. Okay. Now coming to step 5. That's the bond formation of sodium chloride. Now, the bond formation. How the bond formation we will show? How to show the bond formation in a Lewis diagram. This is sodium. This is chlorine. Now we know, as we know that rather metals, or rather we have discussed this one, that metals, they give out electrons as early as possible. Non-metals, they accept electrons as early as possible. So when it is sodium and chlorine, sodium wants to give electrons at the earliest, and chlorine wants to accept that electron at the earliest. So what happens? This electron, as it's shown, you can see that this electron, the electron from sodium, gets transferred. That for that reason that arrow has been shown, it gets transferred from the sodium atom to the chlorine atom, and with that particular one atom, the bond formation takes place. Remember one thing, a bond formation will only happen between two electrons. So minimum, every bond require two electrons to form. That's the minimum and the maximum. So the minimum number of electrons required to form a bond, that's 2. The maximum number of electrons required to form a bond, that's 2. So this is how it looks like. So sodium, Na plus, because why it's plus? Because it has given the electron to chlorine. So the electron is no longer there in the atom of sodium, and hence it is Na plus, because the loss of one electron increases the positive charge, and hence Na plus, and Cl minus, as you can see, because chlorine has accepted one electron, and hence Cl minus, chlorine. Okay, so as you can see, the red dot and the black dot. So the red dot is basically from the sodium atom, and the chlorine is having the rest. So the bond formation between sodium and chlorine has occurred by the transfer of electrons. Now, this bond is something different. Now, there is an interesting thing. This bond is something different. What is the difference? It is equivalent to NaCl. And after that, you can see this blue, there is a double arrow symbol it's given. It's basically electrostatic force of attraction. That's basically as you can see, the plus and minus together. That's basically the electrostatic force of attraction, which is the reason of the ionic bond between the two atoms. That's called an ionic bond because it's forming between ions, cations and anions. So it's an ionic bond. And you also know that due to transfer of electrons, it's called an electrovalent bond. So electrons of the valence shell being transferred, called electrovalent bond. So that's the double arrow represents the electrostatic force of attraction. And physically, and to be precisely, ionic bond is basically no longer exactly a bond. As moving, if you follow the definition of a bond, I stated earlier also that bond is basically formed between two electrons. So the minimum number of electrons required to form a bond is 2. The maximum number of electrons required to form a bond, that's also 2. But over here, it's basically with the presence of the positive and the negative charges together, they attract each other strongly. And thus that leads to the formation of a bond. That's called an ionic bond. So physically, it's not a true bond in the real sense. So in the real sense, ionic compounds are not having a true bond by itself. Okay? So this is the electron dot structure of sodium chloride. Note, there is a note given also that since dots in both elements does not clearly indicate the electrons that have participated in a bond when the structure is represented by a single color, hence other symbols like cross or star or anything else is used. Remember? So since dots in both elements does not clearly indicate electrons that are participating in the bond, since over here I've highlighted, but actually it's an electron dot structure, so we should represent the bond formation and electrons present in every atom by dots. But the problem is that if the elements are represented on a piece of paper with only one single color, then to identify that which electrons have participated in a bond formation becomes difficult. and hence cross or star, some other symbols are used in order to specify clearly that which from where the electron is coming, and what's the way of forming the bond and accepting electrons. The next we are having example 2, similarly, calcium fluoride. You're having calcium fluoride. So we will always now, I hope it's clear to you to how to draw a Lewis structure. So we will follow the steps similarly. Although we'll list out all the elements present in the molecule, it's calcium and fluorine. We will list out the valence number of valence electrons present in each atom of an element. That's the atomic number of calcium 20, valence electrons 2. Atomic number of fluorine 9, the valence electrons 7. So step 3, the molecule in the formation form, reaction form, it is calcium plus 2 fluorine atoms forms CF2. Step 4, draw the electronic structure of the reactant using dots, where dots represent valence electrons, without considering the other electrons of the group orbits. So this is electron dot structure of calcium with different symbols mentioned. It's a fluorine atom, electron dot structure of fluorine. Now, bond formation of calcium fluoride. So this is calcium, and there goes 2 fluorine atoms. You can see over there that the 2 atoms of calcium, the 2 electrons of calcium, the valence electrons, get transferred to fluorine atom, to the fluorine atom, and with that, it forms calcium fluoride with an electrostatic force of attraction, the bond over there, and this is a slightly shorter version of calcium fluoride. Equivalent to CF2. So this is a complete way, this is a complete way of representing Lewis molecules and all the Lewis structures of a particular molecule. Okay, complete way. This is the electron dot structure of calcium. Similarly, we can draw other molecules also. The first, we can draw magnesium chloride. It's shown over there, the structure. We can draw aluminium oxide. That's also shown the structure. We can also draw barium oxide. The structure is also shown over there. So there are different ways, different methods of different ways by which, or ways not, there are different atoms of whom we can draw the Lewis diagram on the electron dot structure. Now, it's a thing that so far we have discussed, or ionic or electrovalent compounds or molecules. We were discussed so far. But what about the covalent compounds or molecules? They can have the wish that they should be represented by the Lewis diagram or the electron dot structure. What about them? Now, for them, we will follow all the steps shown earlier, but representation will be slightly different. That's the thing. Representation will be slightly different. What's the difference? Let's figure it out. We will consider an example. Lewis diagram structure of the electron dot structure of water molecule. All the elements present in the molecule are hydrogen, oxygen. All the valence electrons in each atom of the elements, that's 1. Hydrogen, atomic number of valence electrons 1. Oxygen 8, number of valence electrons 6. Now to write the molecule in the formation reaction form, that's 2H plus O giving to a H2O. With the dots electron representation, that's hydrogen, electron dot structure with different symbols, followed by oxygen, that's electron dot structure of oxygen. So that's step 5, the bond formation of water. So as you can see, that's the atom with the electron, oxygen, this. Now, previously, all we showed, there was a charge, plus, it's a positive charge, and a negative charge. But over here, when the covalent compounds are being focused, covalent molecules are being focused, we are denoting this one as electron sharing. So sharing of electrons is being represented in a covalent molecule. So no charge formation, no ion formation, but molecule formation, but only the thing is electron sharing. This is how it looks like with the bond RH2. So this is electron structure of water molecule. Now, with the bond formation of water, this molecule is also giving us another very prime information. What is that information? We have discussed up till this much. We know this much. We discussed about previously, if you remember, the lone pair of electrons. And this is the lone pair of electrons. Water basically is having two lone pair of electrons. Water molecule is having two lone pair of electrons. Basically, and actually, those two lone pair of electrons belong to oxygen atom. I said, and that one also I mentioned that it is not at all molecule specific. It is basically atom specific. So which atom is actually the central one, the bigger one atom? So based on that and how many electrons it's having, valence electrons, and how many are participating in the bond formation, based on that, the number of lone pairs will be decided. So water molecule is having two lone pair of electrons. Let us consider an ammonia molecule. We'll do all the things. The presence or other elements present, hydrogen, nitrogen, number of valence electrons. So with hydrogen 1, nitrogen 5. Y5, remember that it's basically it is basically the structure that's 2, 5, atomic number 7, 2, 5 electronic distribution, and based on that's 2, 5 valence electrons, and this is a reaction formation mode, represented by dots having nitrogen. So the 5 electrons you can see over there, electron dot structure of nitrogen. Now the bond formation, you can see over here, to the 5 electrons distributed and 3 hydrogen atoms, 3 different positions, and this is how ammonia molecule looks. With every hydrogen atom, 1 electron is bonded, 1 electron of whom? 1 electron of nitrogen, and 1 electron hydrogen. All the way, I think, so 3 bonds. So 3 bonds. Yes, over here you can see 3 the bonds, NH3, and this. So electron dot structure of ammonia molecule. Now this molecule is also having, as you figure it out, that is, as you can figure it out, another primary information which this, or rather this ammonia molecule is giving, lone pairs is, of course, lone pairs, yeah, that's one. Lone pair of electron, and it's having only one pair of electron, one lone pair of electron, only one. 2 electrons means 1 pair, so 1 lone pair of electron ammonia is having. Now, apart from this molecule, there are different covalent molecules also where whose lone pairs, whose Lewis diagram can be is possible. So I will definitely expect you to practice those molecules to the Lewis diagram. And apart from the covalent and the ionic compounds, they're having the coordinate bonded compounds. That means the coordinate bond is another type of bond, and those coordinate bonded compounds also the Lewis structure is possible. We'll go with this, the ammonia molecule, and this is a lone pair of electron, followed by when H plus ion, it's a cation, this H plus, and it's very small size. It approaches, and basically it's with near, it tries to take up this lone pair, because and nitrogen also shares, or rather partially donates this lone pair to H plus, because H plus is having no electrons and it's unstable. And if ammonia gives this lone pair, it's the valence of basically the lone pair of this nitrogen atom is being given out. No, the nitrogen is having basically no such problem until so. Based on that, it is a share, or rather, it's a partial donation to the hydrogen ion, and it forms a bond, and it's been shown that this is a coordinate bond, shown by an arrow sign. can see that's the coordinate bond. What happens is the entire molecule from ammonia, it forms an ammonium molecule and becomes a cation and once again an unstable. There's an example. It's a structure of ammonium ion. And this is what about that the entire molecule is becoming a positively charged species, and definitely it makes a bond with another ion to generate the final stable compound. So with this, I'll like to conclude today's lecture. So with any other queries, you are ask, and thank you so much. For any of more further questions, you are free to ask questions. Until then, take a very good care of yourself. Thank you.